Okay, good morning, Year 12. I'm going to talk you through one of the PowerPoints, which is on the Unit 2.1 page, to help you to understand a little bit about the relationship between concentration of reactants and the rate of the chemical reaction. What is the numerical, mathematical relationship between those two things? How can we describe it? Now, to help, I'm going to scroll down the page a little bit. There's two PowerPoints here. First one, fairly straightforward, a bit GCSE-ish. When you get to the second PowerPoint, this is the one that you've suggested you'd like a bit of help with. Reaction mechanisms and rate laws. It's a long PowerPoint. As you can see down here, it's 35 pages. Pages 1 to 16 are about rate laws, or what we call rate equations, that define that relationship between rate and concentration of a reactant. The latter part of this PowerPoint, so that will be pages 17 to 35, is about mechanisms. And that's a separate idea. The two are, of course, related, but I'd like to deal with those separately for the time being. Okay. So we're just going to focus on rate equations, which define that relationship. Now, I've got this PowerPoint open in a separate page. Here we are. So let's have a look through it together. Now, the first page, the only thing you really need to notice on here is just to illustrate this relationship. We've got a hypothetical chemical reaction here between. Just wait for that sidebar to disappear. We've got a hypothetical reaction here between two reactants, A and X. Okay, so whatever they might be, two reactants, A and X, reacting together to give a product. What we're trying to find out is what effect does reactant A have upon the rate of reaction, and what effect does reactant X have upon the rate of reaction. They may or may not affect the rate to the same extent. And the extent to which each reactant affects the rate of reaction, we assign it a number that we call the order of reaction. So we have a number for reactant A, which is called the order of reaction with respect to reactant A, and we have another number for reactant X, which again is another number which is the order of reaction with respect to X. Now these numbers, these orders, give you a sort of scaling of to what extent the rate of reaction depends upon those reactants. The numbers that you need to know about are 0. The reactants have no effect upon the rate of reaction, which is a bit of a weird thing, which will make sense when we look at mechanisms. So in some cases, concentration of a reactant has no effect. It's a 0 order. If it's directly affecting the rate of reaction, we call it first order, the value 1. And if it has a very strong effect on the rate of reaction, we give it an order 2, and that's a second order. So what we're going to look at in this first few pages is how to establish the order with respect to A, how to establish the order with respect to X. First point to mention right from the outset is these orders can only be established experimentally. You cannot look at a balanced equation and say to what extent it will affect the rate of reaction. The reason being it's to do with the mechanisms of the reaction, and you don't know about that just by looking at balanced equations. Nobody does. Okay, so we can only find out this relationship by doing experiments. Typically, things that you might do if you just got two reactants, you could do this type of experiment, have one or other of the two reactants in a very large excess. So changes in its concentration have no overall effect because they're negligible. But if one of the reactants is present in a much lower concentration, then the rate of reaction will be affected by that one. So we can independently investigate one reactant or the other. And that's what's being described here. So I'm going to skip over that, and let's just focus then on the outcome. So here, experiments are being carried out in which we're looking at the effect of concentration of reactant A upon the rate of reaction. Now, what's being shown here is, if we can just scroll at a fraction, the concentration of A as time is passing. So as this reaction is proceeding, the concentration of A naturally will be going down because A is getting used up, converted into product. So of course this line will go down. Now you can also just begin to see that it's starting to curve. And if you were to follow this reaction all the way to completion, as the concentration of A goes down, it starts off steep, gets a little bit flatter, and then flattens out and eventually becomes level when its concentration isn't changing anymore when the reaction is finished. Generally, its concentration will go down to zero if the reaction is complete. Remember, as the concentration is getting used up, as the concentration of A is decreasing, the frequency of collisions will also decrease, and therefore the rate of reaction will change. So in this type of experiment, if we want to know what is the rate of reaction with this concentration, 4 molar, the initial concentration up here, 4 molar, we only want to know, well, what is the rate of reaction at this portion of the line? So we don't need to follow this experiment through to the end. This is what's known as an initial rates method. Now, the other thing just to remember here is the steepness of that line is a measure of the rate of the reaction. Steep line means a high rate of reaction. Less steep line means a lower rate of reaction. And a horizontal line with a zero gradient means no reaction is occurring. So the gradient of the line is the rate of reaction. And if you're working it out, the steepness of the line as rise over run, change in concentration of A divided by the time taken gives you the change in concentration per unit time, which is what the rate is. So the gradient of the line is a measure of the rate of reaction. Now, to get the gradient at the start, what we need to do is draw a tangent to the curve at the early part of the reaction here, as close to the zero time as possible. So this dotted line here represents a straight line, a tangent, just touching the curve. And we can easily then calculate from the straight line the change in concentration divided by the time taken. Easiest way to draw it is normally to complete this as a triangle either here, so you've got the time taken for that change in concentration, or ideally extend the tangent so it crosses both axes. So you can look at this change in concentration divided by this change in time. Okay, so we're looking at tangents to give us the rate of reaction. So the first experiment was carried out using 4 molar A. In the next slide, it was carried out with half that concentration of A. So the same idea, the experiment is set up with half the concentration of A. It's left to run for a little while. A tangent is drawn near the beginning of the reaction to work out the gradient near the start of the reaction. That's the initial rate. In this case, it's 0.3. And then one further experiment, which the concentration is halved again. So it's gone from 2 down to 1 molar this time. And again, to find this rate of reaction, a tangent was drawn touching the curve close to the zero time to get the initial gradient, the initial rate of reaction. So that's fairly straightforward. That's quick to do in the lab. It's fiddly because you've got to set up 3 separate experiments, but they're fairly quick because you don't need to let them run to completion. An alternative way of getting that information that you can see in the table here, the concentrations and the corresponding rates, is by doing this type of experiment, which is what's known as a progress curve method. So you set up one experiment. In this case, the initial concentration was 4 molar up here, and then we let the experiment run. Concentration of A goes down, becoming less steep, down, 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 and then eventually flat when the reaction has finished. In this case, not quite at zero concentration, but the reaction appears to have stopped. Okay, so from that, which is one single experiment, but takes more time because it'll slow down as it approaches the end, we can extract the data we need from one curve. We draw a tangent near the beginning, and at the beginning it was 4 molar, and the tangent, the steepness of the tangent is 0.6. That's the rate of reaction. A second tangent has been drawn sort of on this part of the curve here. Now the concentration there, we just read across. Where the tangent touches the curve, we read across to the y-axis, and then you've got the concentration at that point on the curve. It looks like here that was 3 molar at that point on the curve. And the rate of reaction, this number, is the gradient of this line, which again you can get by drawing a triangle, dividing change in concentration by the time it took. And then one further tangent has been drawn down here, close to the end. This tangent here, much flatter one, from the point where the tangent touches the curve, read across to the y-axis there. That'll give you the concentration at that point on the curve. It looks like it was 2 molar. And the rate of reaction at that point on the curve is the gradient of the tangent at that point on the curve, which has been worked out for you there is 0.3 molar. Okay, so using either of two methods, initial rates method or progress curve method, we have established a set of data. We've got concentrations of A and the corresponding rates of reaction. Now, if we look more closely at the data, which is the same from both of those two experiments, as you can see, 0.15. No, it isn't the same from both those sets of data. I take that back. But you can see the same pattern. 4 molar, the rate was 0.6, and 2 molar, it's half that, 0.3. And half that again, 1 molar, the rate is halved, 0.15. So the data, even though the values are slightly different, we've established the same relationship. From the progress curve, 4 molar, 3 molar, 2 molar, as the concentration is halved from 4 molar to 2 molar, you can see that the rate of reaction is also halving, 0.6 to 0.3. Now, what's this telling us? This is actually telling us, I'm going to flick to a separate document for a moment. Now, this is one that was shared this morning in our team forum. This is the summary IB document that you looked at. This is the sort of graph that you could then plot with that data. If you look at the axis of this graph, this is the rate of reaction, and this is the concentration of A. And as you can see, if you plot them, it's a straight line that passes through the origin, 0. This means we have a constant gradient for this line. In other words, if we divide the rate of reaction by the concentration, we get the same value every time. It's a constant. Rate divided by concentration is a constant. So I'm going to go back to my PowerPoint if I can find it. Okay, so bearing in mind rate divided by concentration is a constant. If we were to write rate divided by concentration of A is equal to a constant, and then rearrange it, multiply both sides by concentration of A, you would derive this simple equation. Rate is equal to a constant times concentration of A. This is our first little bit of a simple rate equation. This isn't the full rate equation for the reaction. This is the rate equation for reactant A only. Now, this number here, you're possibly wondering, where does that number crop up from? 1. To be honest, you could leave that number out. It doesn't mean anything here because A to the power of 1 is equal to A. The value for the concentration of A to the power of 1 is just equal to the concentration of A. So that number, in fact, you could just omit it, leave it out when you're writing this expression. But it's helpful to just bear in mind that there is this kind of implicit 1 there, because what this is telling us is that the rate of reaction is proportional to concentration of A to the power of 1. And that's what we call a first order relationship. This reaction is first order with respect to to the concentration of reactant A. Putting units in, concentration of A has units of moles per dm cubed, and the concentration of rate will be moles per decimeter cubed per minute or per unit time, because remember rate was from the equation we saw it as change in concentration per unit time, so it's moles per dm cubed per minute. So if you want to know what the values of the rate constant are, it would be rate divided by concentration of A to give us the K. So rate divided by concentration of A, the mole dm cubed bit cancels out, and the units of K, the rate constant, will just be per minute, min to the -1. Okay. So according to the data that we've been given in this table, all we can see is this reaction is first order with respect to reactant A. There we are. And then that's basically just repeating. Now I'm going to scroll down a little bit, because remember we've got a second reactant here. We also had reactant X. So similar things can be done. This looks like the initial rates method. So an experiment was set up with an initial concentration of X, sorry to be flicking around there, initial concentration of X is 3 molar, and the gradient of the line was worked out to be 0.6 at the start. In fact, you can see this one, unusually, it appears to be a bit of a straight line, which is a bit odd, isn't it? Because normally these things, collision frequencies go down, you normally see these things sort of curve off. This one appears to be a bit straight. There we are. That's what it is. Can't lie about the data. It is what it is. As I say, you can only establish orders by doing experiments. So we just have to see what we get. So a second experiment now has been set up with concentration of 1.5. In other words, half what it was in the first experiment. 3 molar concentration of X in that experiment. Half that, 1.5 molar concentration of X in this experiment. And again, the gradient of the line at the initial part has been worked out. Rise over run, change in concentration of X divided by the time taken. That's been done for you. There's a value of 0.6 there. And then a third experiment, perhaps. We halve it again. So half 1.5 is 3/4, 0.75. So we've halved the concentration again, and that's what the data looks like. We don't need to let it run until the reaction is complete. So we've got the initial gradient of the line here with an initial concentration of 0.75. Now, as you can see, for this one, it's a bit unusual because initial concentration 3, 2, 1, 0.5. Look at the values of rate of reaction. They are unaffected. So even though, as the concentration of X is going down, the rate of reaction is not being affected. That's not something that you would have expected or been able to easily predict based on collision theory. The reason for this is going to be something to do with mechanisms. We'll do that separately later. But what can we say about the relationship now between X and the rate of reaction? In other words, what is the order of reaction with respect to X? Now, we've just seen that we can write this structure of an equation for a rate of reaction for each of the reactants. Rate is equal to a constant times the concentration of the reactant raised to the power of a number, which can either be a 0, a 1, or a 2 for your purposes. Now, in this case, as we're saying up here, rate is proportional to x to the power of 0. Rate is proportional to x to the power of 0. What does that mean? Well, if you take the numerical value of the concentration, whatever it is, raise it to the power of 0, what do you get? Well, a value raised, any number raised to the power of 0 should give you a value of 1. And therefore this expression here simplifies. This will become k, the rate constant, multiplied by 1, which is just the rate constant, if you just times it by 1. So this whole expression becomes much more simple. It doesn't matter what the concentration of x is, because to the power of 0, this will become 1. So in every case, rate will be equal to k, and that's it. The rate constant is a constant. So rate is equal to k. Now in terms of units, in this case, if we have here rate in moles per dm cubed per minute, and it's equal to just k, this bit has disappeared because it's become 1, then the rate constant must have the same units, moles per decimeter cubed per minute. So it's more simple. Now, for the purposes though of establishing the order, because rate is proportional to x to the power of 0, we say this reaction is 0 order with respect to the concentration of x, which is what you can see here in the next slide. Okay. Now we've actually got two pieces of jigsaw puzzle now. We've looked at A and we've looked at X, the two reactants separately. We can now put the two together. And this is what we call the overall rate equation for the reaction. The overall rate equation. Now you could write it in this form. Rate is equal to rate constant times concentration of A to the 1 times concentration of X to the 0. Or, again, bearing in mind that this simplifies just to the value of 1, x to the power of 0, you could just write it as this. Rate is equal to rate constant times concentration of A. And remember, you can even just omit this value 1. You don't even need to write value 1 there. If you just write concentration of A, that means, first order, means 1. So it's first order with respect to A, it's 0 order with respect to X. One other expression that we can sometimes use is what is the overall order of reaction? And that's quite simply the sum of the separate orders. So we add up what's the order with respect to one reactant plus the order with respect to the others. And in this case, it's just 1 plus 0. So overall, this reaction is first order. Now this is written here and underlined in red. I said it right at the start. It's really important. I wanted to say it from the outset and mention it again at the end. You can only find this type of rate equation, or what we sometimes call the rate law, by doing experiments. You can't predict this by looking at the balanced chemical equations. Now, in a separate screencast, we're going to have a think about this. Once we know what the rate law is, what the rate equation looks like for a given reaction, what does that tell us about the mechanism of the reaction? What steps are involved in the conversion of reactants into products? It actually sheds a light on that and helps us to understand what's going on. It also solves the mystery of how can something possibly be 0 order? How can a reactant concentration not affect the rate of reaction? The mechanism holds the answer to that. And this we will look at in the next screencast that I do for you. Now, I hope that was helpful. Perhaps rewatch it, and if you're still not sure about it, then please send me a message. We can chat in the team forum, and let's see if we can sort this out together. Okay? Hope that helps for now. Thanks so much.